So don't worry too much about using ABL. If you want to use ABL to like ensure that you have really good runtime, go for it. Just there is that extra risk of making it so that way you don't accidentally do invalid locations and cause your program to crash. So just be cautious. But you should be able to, I will try to make it, I will make it so that way the binary search trees non-balanced work. But yeah, I'll construct the data so that way it's not terrible, and I'll try to upload a reasonable size input before the end of the week. It might take me a little bit of time to get it. So that's the first thing I wanted to talk about that's not related to the topic for the day. The second thing I want to talk about that's not really related to the topic of the day is the exam that you guys took. And so there is two questions I really wanted to go over in particular. One of them is how do you do post-ordering evaluation, or how do you basically construct a case for post-orders? And the other thing I really wanted to go over was how do you find maximal length trees? So both of them are actually kind of weird because they're both constructing trees given partial information. And you guys actually had a lot of difficulty with it, which is okay. It's not a terrible thing. But the thing is, like, the ability to construct these test cases, like the one I'm asking you, is really useful for when you're trying to actually develop cases for breaking your program when you go out and about. Because if you can figure out all the horrible things that some user can do to your program, you can try to figure out what you can do to circumvent those problems and to mitigate any issues that you run into. So let me just go ahead and really quickly pull up the questions. That way I can refresh myself. That was not the right thing. So the first one was draw a DST whose post order traversal is 1, 3, 4, 2, 7, 9, 8, 6, 5, and 10. So the one thing that hopefully all you guys got out of this is that the root is 10. All right, cool. Now, why is the root 10? Yeah, the last element is always going to be the root. And that's regardless if it's a BST or a BT. So you don't have to really worry about what we're given. If I say the post order is this, then you should immediately say 10 is the root. Now, how do we do the rest of this? And really, it's kind of complex and hard to figure out. But because I say that this is a searchable tree, you should be able to actually figure out what's going on. So if this is a searchable tree, where should the other nodes be with respect to 10? Yeah, they all should be on the left-hand side. And so that should have been like your first clue as to how to draw the rest of this tree. And now the question would be for you is, if this is the remaining post order, what do you think this next node will be? 5? Why would it be 5? It's the last item left. And really, when you can think of it, is when you're doing a post order traversal on any tree, what's going to happen is you're going to have the last element, which is the root, and then you're going to have some sequence over here separated by some sequence over here. And I know that sounds really weird, but the idea is when you're doing a post order traversal, you go to the root, then what you do is you go through and you output everything in here, and then after you've printed out everything in this side here, you go into the section over here and print out everything in here. Everything that gets printed out in here will occur in this section, and everything that gets printed out in here will occur in this section. And now, the idea is if you can find out where this breakpoint occurs, you can actually figure out kind of how this tree has been structured. And so the thing is, since everything should be in this section here, then the idea is that this is going to basically be an empty area because the root was 10, and nothing is going to be larger than 10. Everything else has to be in here. And moreover, what this is here is actually just a post-order traversal on whatever this node is here. And since we're doing a post-order traversal on whatever this node is here, and we're working with basically everything that's not 10, then that means we're working with a post-order traversal of 1, 3, 4, 2, 7, 9, 8, 6, and 5. And since the last value in a forced order traversal is always the root, that means we know that 5 needs to be the root of this subtree. And so now that we know that 5 is the root of this subtree, we need to go ahead and figure out how to split it into 2 groups such that one group is all less than it, or on the left side, and then the other, or the right side I should say, and one element, all the other elements are on the other side, or the right side. So how can I split the remaining post order so that way I have all the elements over here are greater than it, and all the elements over here are less than it? Yeah, so the elements that are greater are going to be 7, 9, 8, and 6, and so it should be these guys. And the elements that are less than are going to be 1, 3, 4, and 2. And so I should be able to do the construction with this. And so now what I need to do is figure out how to do a post-order traversal on these elements. What would the tree be for this guy here? 6 would be the top element. So 6 is the top element, and now I need to figure out how we would split 6 into a left and right subtree. How would these elements go into the left and right subtrees? Yeah, so this would be empty, and then these elements here would be on the other side. And so now I need to figure out how to do the 7, 8, 9, 8. All right, and now how do I split the remaining elements? So 8 is, yeah. So we have to have, unfortunately, I didn't get myself in the room here. 10 would be here, then 5 would go down here, 6. We agree that 8 is going to be here. 9 has to go on this side here, and 7 has to go on this side here. And this is what that section looks like. And now we need to work with this 2, 4, 3, and 1. So what's going to be the root of the subtree? And how do I split the remaining elements? So now how do I do the left subtree? Yeah, 4 is going to be the element because it's the last element in the list. And now how do I do this one? And this should be what it looks like. And if you want to double check their work, you can. So what we do is we'll do a post-order traversal on this. So we go down, 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 down. Now we're leaving 1, so what do? We output it. So we go up to 2. Do we output 2 now? We have to do what? Go down to 4, we go down to 3. We output 3, right? And then we go up. Now what do? We output 4 because we're leaving it. And then we output 2 because we leave it. Now what do we do here? Do we output 5? We need to go down. We don't output 6, we have to go down. We don't output 8, we have to go down. We output 7. We go up to 8. We don't output 8, we go down to 9. We output 9 because we're leaving it. We go up to 8, what do? Output 8. And now what do? Because we go to 6, then we output 5. And then once we leave 5, we have to output 10. And so is this sequence here equal to this sequence here? 1, 3, 4, 2, 7, 9, 8, 6, 5, 10. Now, as it turns out, any VST, like any different VSTs, will always generate different post-order traversals. So there's always going to be only one, like if you have the post-order traversals, there's only one VST that applies to it. But sometimes there might not be a VST that applies to it. There was an example of that happening on the practice exam. And if you work through that exam, you'll understand why that's the case. I don't really want to cover that right now. I just want to kind of go over how you can go about doing this problem. And now the other problem that a lot of you guys ended up not doing the best on, and in fact, I never saw a correct answer on it when I was like looking through the exam. So I don't know. That's probably not a good thing. Is question number 8. Yeah, the one that talked about the non-null children. So the question was, what give? Give an insertion give an insertion order of 9 elements, basically of the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, such that the VST generated, oh god, that's a long question. And I was hoping that people would actually read this problem incorrectly and end up getting it right. I know that sounds really weird. So when I said has maximal depth, I was hoping that people would be like, oh, I need to make it as deep as possible, and then make sure that I satisfy the other property. But really what it's asking is satisfy the left and right children property, and then make it maximal afterwards. And unfortunately, that's how most people read it, and then they ended up doing it wrong because of that, because they didn't see the better construction for this case. And then we want the number of non-null left is equal to number of non-null right. All right. So I'm going to make this a little bit simpler, and we'll try to figure out what the answer is. What if I had only 3 elements? What if instead of doing that long thing, I did this? What would your guys' answers be? Yeah, so you can do that, and then you can do this. You can also do 1 over here, and wait a minute, this is not right.
Yeah, that's not what I was saying.
Why did someone say 2, 1, 3?
No.
I was hoping for. Yeah, so some people would put 2. God. Yeah, some people put 2, 1, 3. And what this ends up doing is when we insert these nodes into the tree, we have 2 here, we have 1 here, and then we'll have 3 over here. But unfortunately, this won't create the maximal depth tree. Because really what I'm looking for, in one case you can have, is something like this. We've seen these structures before in our BSTs when we're working with ABL trees. And so we just say that this is the design we want. We can go ahead and try to fill in the values that will make this design be possible. So what this is here is this has to be the largest element of our tree. And the reason why this has to be the largest element of our tree is because every other element is inside the left subtree, which means that this element has to be 3. And now, looking at the remaining 2 elements, this element has to be smaller than this one. So this one has to be 2, and this one has to be, or 1, and this one has to be 2. So this one, unfortunately, doesn't have a maximal depth. But in this one here, we have 1 left child and 1 right child that are non-null, and we have no other non-null children. And because of that, the number of non-null children that are on the left is equal to 1, and the number of non-null children that are on the right is equal to 1. And so we have ideally a balanced tree here. Some people, what they did was they misread this problem, and I tried to correct this during the exam, but a lot of people like the number of children on this side needs to be equal to the number of children on this side, and then it needs to happen recursively. You can't do that recursively. And the reason why we can't keep going recursively is because in order to have that property hold, this would need to be a perfectly balanced tree. And unfortunately, the only way to have it, well, I mean, in this case, it's a perfectly balanced tree, but you can't do a perfectly balanced tree with the numbers that were given to you. And so I really tried to tell people the correct direction to go if you misinterpreted it, to go ahead and come up with something that has the number of elements that are on the left and the number of elements that are on the right throughout the entire tree are equal, and not strictly inside these 1 subtrees. And that was a little frustrating for me, and I'm sure for you guys as well. So this is just a really simple example of how we can end up with a really nice structure with 3 nodes. Is there any way you guys think that we can extend this to more than 3 nodes? What if I said we had 5 nodes instead? Yeah? Question?
I'm confused. Which one of those is correct?
Oh, yeah, sorry. This one is the larger depth. This is the depth of 2. 3, I guess if you can think of it, is a depth of 2.
Why does that meet the requirement?
This meets the requirement because, so the number of non-null left children is 1, because there's only 1 of them. This is the left guy, and then this guy is the right guy. And so the number of non-null right children is 1 as well, because there's only 1 right child in the entire tree. And so because these 2 numbers are equal, this one is going to be a valid tree by the stance of, by the condition is that the number of children are equal. And it's also going to be a larger depth than this one here. Because the depth on this one here is only 2, while the depth on this one here is 1 deeper. This is if you were constructing an ABL tree, and you had this inside one of your subchildren, and this is as your other subchild, this would be a deeper child, and this would also be unbalanced. So you'd actually need to redo this one, or rotate this one to fix it.
So it's not the total, and it's not in reference to the root element as far far as non-null, the number of non-null left and right?
Yeah, it doesn't say anything about with respect to the root. It just says that the number of non-null right children is equal to the number of non-null left children. Again, I did try to clarify this in the exam to people that were confused, and I don't remember if I put something up on the board at one point about it, but it was a little bit unfortunate that this ended up happening. A lot of people just misunderstood the question because of that. It ended up being wrong, which is not a terrible thing as well, because not many people understood the question. It means that this is going to be a really low point question, and it's almost going to be negligible to how it affects the exam grades. Yeah, right, it's like when everyone misses something, it's like no one missing it. All right. But anyway, so we're going to extend this to having 5 nodes, just really simply. So if we have this weird structure where we kind of zigzag, we're going to go ahead and try to create a zigzagging structure inside a depth of 5. So what we're going to do is we're going to alternate left and right children. And so this here, there's 2 left children now, and there's 2 right children that are non-null. And so in order to build this, this one has to be the maximal element. This one has to be the smallest element of the remaining elements because everything is on the left subtree. So this has to be 1. This one has to be the maximal element of everything else. So this is 4. This one has to be the minimal elements of everything else. So this is 3, or 2, and then this one, the last one, is going to be 3. And so the insertion order would be 5, 1, 4, 2, and 3. So all we need to do is we need to just keep adding like an extra zigzag, and we can go ahead and increase the depth of our tree. Notice that the number of lefts is 2, and the number of rights is 2 as well. So we're good on the left-right thing. So we're just going to go ahead and keep doing this until we get to 9 values. So this is 5, 7, 9. And so this element here needs to be the maximal value, which is 9. This one needs to be 1. This one needs to be what? 8. All right. So this is all you ended up needing to do. There's actually more than just this, though. What you can actually do as well is another interesting way to do the construction. You can also do this very funny-looking design. Does anyone want to try taking a guess as to what these numbers are? All right. And what's this one? 8? I heard someone say it. All right. 5? Yeah. Yeah, so these are 2 ways you can do it. The number of left children, or there's 1, 2, 3, 4 left children, and there's 1, 2, 3, 4 right children. Again, don't worry too much. A lot of people ended up missing this. So if you put something down, you're going to cut it as long as it's like an actual insertion order. If you gave me garbage, you're going to get garbage. But we are doing partial credit on this one, so don't worry too much. And not many people got it correct. So also don't worry too much about that problem. But I just figured to kind of show you how to do it. I guess one question I could ask, ignoring the left and right children constraints, how many maximal depth trees are there in a graph, in a BST? So how many maximal depth BSTs of n nodes exist? So what we can do is we can very easily, like the most common one that we all know of is this one, right? Where it goes down however many times you need. You can also very easily look at the other way where we did the thing on the opposite side. There's n nodes that way. And so these are like 2 ways you can do it. And I also just showed 2 constructions. I think you guys all agree that the reverse of these 2 would also work, right? All right. So now the question is like how many of these actually exist with the n nodes? So if we think about it, when we want a maximal depth, we know that each node that from where we're at is going to go either to the left or to the right? All right. Now, how could we potentially enumerate if we know that each node either has to go to the left or the right of the last node you inserted? You never want to insert somewhere further up on the tree. Like when you have some tree that you're building that's supposed to be maximal length, you never want to insert another node up here. You always want to insert at the last node. And you always will have these two options to take. So do you guys have any inkling, any ideas to how to count the number of trees? So someone said n minus 1. Unfortunately, that's not going to be quite what you need. And the reason why is because if you had one node, then this is maximal, and that means there's one value. N minus 1 would be 0, so that can't be the case. Maybe it's n. Well, let's go ahead and try n as our potential thing. So I can have a tree like this for 2 nodes, or a tree like this. So there's 2 ways to do a 2-length tree, and there's 1 way to do a 1-length. So this actually seems pretty good. When I get to 3, how many ways is there to do it? Why is it 4? So we know that this one was one way. We know that this one is the other way. Okay, so it's not 3. Out of curiosity, how many ways is there to do 4? Does anyone know? Yeah, that's actually it. So all we need to do is take any one of these trees here, and we can insert a node to the left, or we can insert the node to the right to go ahead and form a new one. And so every single one of these trees can correspond to 2 additional trees that are maximal depth. So it's always going to be p of n, or like whatever this is going to be called, is equal to 2 times p of n minus 1. And so if you think about this, and you end up performing a recurrence relation on this, and you solve it, you'll find out that this is very simply, and of course you know that p of 1 should be equal to 1. This ends up resulting that p of n is actually equal to 2 to the n minus 1. So it's not that bad. If you want to actually solve this recurrence relation, it can help you out a little bit for the final exam. It's a pretty trivial one to do, but you know, everything is worth the effort, I guess. So I'm going to go ahead and begin talking about what we're actually supposed to talk about today, which is going to be sets. So we've actually discussed a little bit of sets already, so this hopefully will be more of like a refresher, and I'll begin talking about the different ways we can do sets, the different things we can use sets for, hopefully, a few other things, maybe. One thing that's really nice to do with sets is for doing like verification. So if you wanted to potentially have a list of employees that are working for you, and you want your employees to be able to come in and swipe a card so that way they're actually able to access the building because maybe there's sensitive things inside there, you'd want to go ahead and store the list of these employees' identifications, like ways to verify it's actually your employee inside some data structure. And what we normally would think about storing these in is like some set. Maybe you're going to be storing like their name, or maybe you store like a fingerprint or something weird like that. You'll go ahead and store all of these like big complex things inside some data structure. And one of the things that's really nice about this thing is that if you have some employee that's like, or some person that's saying, hey, I'm an employee, you want to be able to quickly verify that that person actually belongs to the set by taking your identifiable information and confirming that it's inside your set somehow. Now this isn't like how people actually probably implement something that needs to be secure, but this is like just kind of a high level idea of what we want to do. And so you can think of it as like the employee example for doing these sets things, where we want to be able to confirm that some person is contained or some person exists within the set of employees we have. And so if we're able to go ahead and confirm if someone exists or confirm that they don't exist, then that means that we've implemented what's known as the contains function. Now I've talked about the contains probably a lot. How do we do the contains inside a binary search tree? Do you guys remember? So if we're like trying to check to see if some particular data value, like maybe 7, exists inside a binary search tree, what would we do? Okay. Yeah. So we have to explore the tree, and we would check to see if the top value is similar to or equal to this value. And if it is, then we know that it exists. If it doesn't, we have to either go to the left or the right, and it's based off of what this value is with respect to the head. If the top node of the tree is too big, then that means we need to go to the left. If it's too small, that means we need to go to the right. And we keep repeating this process until we found the value, in which case that person doesn't exist, or we end up not finding the value, and then we know that person doesn't exist. Now, you can go ahead and do one of these data structures, one of these sets with something else. One common way you can, or one other method you can use to do it is using an array of values. So, and we can imagine that this is an unsorted one. And so what's the runtime if you're trying to check to see if a particular value exists inside an unsorted array? We'll go with the average case. Yeah, it's going to be big O of n. And the reason why is because you're going to need to look through approximately half of the values, assuming the value even exists in your array to begin with. If it doesn't exist in your array to begin with, then that means that it's going to take O of n because you're going to have to go through every element. Otherwise, if it does exist in your array, it's going to be n of divided by 2, but we remove those constant factors. So this is, unfortunately, kind of slow. We don't really like this. If it was a sorted array, what would it be? I'll just say array sorted to keep my thing the same. And this is average. Yeah, and the reason why can we do log of n? Yeah, we can do a binary search on the array, and that will give us the O log of n capability. What's the worst case runtime for a sorted array? I heard, I can't spell. I heard two different answers. I heard n and log of n. We'll go ahead and just pull the class real quick. Who here thinks that it's O n? Raise your hand. All right, who thinks that it's O log of n? Raise your hand. A lot more people. So yeah, it's going to be O log n in the worst case. And the reason why it's O log n in the worst case is because the binary search always reduces the amount of things you're looking at by 2, assuming you're able to get to the middle point of your array. If you're able to get to the middle point of the array, and it's very easy to do that if you have a sorted array and you know the length of it, then we're able to always eliminate half the values. Always eliminating half the values means that we're able to get very good performance, and we're always able to find it in a logarithmic number of times. So the sorted array actually works really well. What about the BST? What's the average case for the BST? Yeah, it's going to be log of n. And the worst case in the BST? Yeah, we just went over today. It's going to be unfortunately big O of n. So it doesn't have the best performance. But what did we do to fix this issue? Yeah, we did a balanced binary search tree. And so the average case in the balanced binary search tree is what? And then what about in the worst case? Yeah, it's still big O of log of n, even though it might be a little bit bigger than what actually log of n is. And the reason why is because you might not have perfect balancing. We don't really care about the tree being perfectly balanced in the ABL tree, right? It just needs to be somewhat balanced. But that's okay. And this is going to be in the worst case scenario. All right. Let's see. And then another method that people tend to talk about, there's two methods that we're not going to be able to cover immediately. They're going to be done in future lectures. But the linked list, so what would be the linked list contains? Average. Yeah, it's O of n, unfortunately. And the worst case is going to be identical for this one. But we don't really care about it because it's not very good. Okay, I cannot spell worst like half the time today. And then I put the O in parentheses. Okay, big O of n. There we go. All right. So this is the contains method. What other methods did I say the set should have? This was like a couple of lectures ago. Hopefully you guys remember. Yeah, the insert. And so you can think of it this way. If we're having the employee example, we want to be able to, at some point, potentially add an employee, right? I mean, if you're never going to hire employees, you're probably going to have a pretty bad company, or at least it's not going to scale well. I mean, there are some companies that can get by with never hiring people, but like, unless you're a mom and pop shop, that's not going to really fly. So, you know, eventually mom and pop might want to add some kids to the store as well or something. I don't know how that works. This is speaking from bad experiences. Please don't ignore child labor laws when you get into business. So, in turn, the other function that's really popular or that's overly useful and pretty much always implemented when we're using sets is the insert function. So, when we're looking at the examples we talked about, there is the unsorted array. And so the unsorted array, what's the average runtime for an insert?
Order 1.
Yeah, it's order 1. And why is it order 1?
You're not inserting in a particular order, you're just inserting.
Yeah, we can just put it at the end. And putting things at the end of a list or at the end of an array is very useful and very easy. And so normally what you need to do with this though is that this can't be strictly speaking a static array. This needs to be some dynamic memory. So normally an array is a bad word to use here. I like to, instead of using array here, I like to use the term array list. An array list basically means that it's an array that will dynamically size itself. We've actually coded a few of them in class, and hopefully you coded one on the boat project, where you go ahead, basically every time you insert an element, you check to see if it's going to go over the capacity. If it is going over the capacity, you'll allocate extra memory and then insert the element. But the idea is that the average case will be no more than order 1. What about the worst case? So this is where it gets a little tricky. And the reason why is because if we're using an array list, then that means it needs to be able to resize itself. And so depending on how you end up doing this resizing, it can change here. But the idea is that if you're resizing memory, it could potentially take size of the entire memory that you're inserting into. And so that means that you could technically have a worst case that's order n. And that's a little bit damaging. But the thing is, you don't really have many of these resize events occur. In fact, over the lifetime of the array, you only have roughly a logarithmic number of resizes occur. And each one you might say, oh, it's about order n, so that means it should be n log n. And then on average of the worst case, which is the weirdest thing ever, it's going to be log n time. But actually, because of how the summation works, it ends up being a geometric sequence, which you guys don't really know what that means. And it ends up turning into 2 times n. So the average of the worst case is considered big O. And amortize is a word that you guys will probably see a lot if you end up going into computer science too. So it's something I'm going to probably address right now. So we're going to call this amortized big O of 1. And I'll try to go over this a little bit more later in the lecture. But I just want to just bang out these 3, 4 functions of the set. So now we have a sorted array list, And so what's the average runtime? Yeah, it's going to be unfortunately order n. And the reason why is because if it occurs somewhere in the middle of the list, then what you need to do is you need to move over a lot of elements. And unfortunately, there's not a really elegant way to do that with computer science. And even if you were able to move over the back half of the elements, the thing is you're still moving over a quarter elements on average, and a quarter of the elements on average is going to be order n. So unfortunately, it's still not a very pretty runtime. What about the other worst case? Yeah. Not much difference going on there. The binary search tree? Remember, this is for the insert. Yep, log. Worst? the balanced binary search tree, and the worst case. So the worst case ends up working out really well in the balanced binary search tree, which is why we tend to encourage using this over the regular binary search tree. And I know, again, on average, this is going to work out really well, but the thing is, you want to make sure that it's going to work well, like, for every person that's using this. Like, if you have 1% of your employees really pissed off, it's not going to work well, because most likely those are the ones that are going to write the reviews. What's up?
You say in a program, you don't have to use like balance, but it saves runtime.
So it does save runtime. I will make it so that way you don't need to use it in assignment 4. But really in practice, you should be using the balanced binary search tree. I'm not going to force you to use the balanced binary search tree on this assignment because then I'll probably have to give out a lot of 50% on this, and I don't really want to do that. I mean, I won't give out 50% probably. I imagine that if you guys implemented balanced binary search trees, you'd probably get about half the test cases right. But the thing is, a lot of people will probably not submit anything if they're trying to implement the balanced binary search tree, and I don't want that to happen. So I would recommend you guys trying to implement just the regular binary search tree, submit that, and then if you have extra time, work on the balanced one. But again, it's not going to be required to get 100%. So that's like the motivation for you guys not to do the balanced binary search tree. Is there another question you have there? Okay. Is there any other questions right now on this? No? All right. And so then the linked list is the last thing we really have. What's the insertion into linked list? Okay. And the worst case? Order n? How would you do order n? So the thing is, the linked list might not be sorted. I probably should have said unsorted. Yeah, at least you would hope. And the reason why this might not be correct, and it's a really terrible reason, is because of the removal. So when you're removing an element from a set, you basically want to say that this element no longer belongs to the set. The idea is that your insertion should insert the element only once into a set, and then whenever you remove that element no longer exists. If we, I know this sounds terrible, if we had 3 people named Joseph that worked at a company, and we ended up saying, hey, Joseph quit, let's go ahead and fire him, and we decided to delete him or remove him from the set, then that means nobody named Joseph will probably be able to get to the office anytime soon, because we would want to prevent this Joseph that we fired from getting in, which would not be a good thing. But the idea is that when you remove one of them, you should remove all instances, and you need to make sure that that element is no longer in your set. And so, really, if we're inserting an element and you want to make sure that you're not inserting any duplicates, you would actually want to check to make sure that there are no duplicates of this element that you're inserting. Because if you're inserting an element X and X already exists in your linked list, then that would be dangerous. So what would be a more correct thing to probably say is you need to go ahead and put some definitions really on this linked list, which do we allow duplicates? So if duplicates are allowed, then that means that we're able to go ahead and do this order 1 insert. If we're doing a linked list though, and this is again unsorted, and duplicates are not allowed, then that means we need to double check that this element doesn't exist. And so this actually will change the array list version as well. I was doing this array list assuming that duplicates were allowed. But if you wanted to make sure that duplicates are not allowed, you would have to do something else. Duplicates are not allowed. You'd have to do something else. All right. The sorted is still going to be roughly this time because this is a really bad runtime. The binary search tree is also going to be this time because the contains is still that time. The balanced binary search tree is always like really nice because the contains and the inserters are always the same. And then the linked list, we don't really care about the use, so that's correct. And so really this is kind of conflicting. Sorry, this is not order 1 anymore, this is now order n. This here, is this order 1? So if no duplicates are allowed and our linked list is unsorted, is it still going to be order 1 to insert? So some people might argue, well, what if it's the first element of our list? Then won't that take order 1? Because then we'll see that it's there and we don't have to do the insertion. That's really good analysis, and that would be correct if you were thinking about a best case scenario. But the thing is, this element could be anywhere inside our list when we're inserting a duplicate. And because it could be anywhere in our list, we need to think of the average case of it being anywhere in our list. So if we're thinking about the average case of being anywhere in our list, it could be at the beginning of our list, it could be in the middle of our list, it could be at the end of our list. And so the idea is the number of operations it's going to take is going to be either 1, and then there's a 1 to n chance of this happening, or it's going to take 2 because it's going to be at the second position, and there's a 1 over 2 n chance of this happening, or it's going to be 3. This is like average for the linked list. So this is at the first spot. This is the second spot. This is the third spot. And the thing is, it could go all the way to the last spot in the array. So what is this equal to? So we need to think about this in terms of summation. We're going to go ahead and bring up something that we haven't done in a while. We're going to go back to the first section of the class, and we're going to go ahead and try to write this as a summation. What is this summation of? Because every single of these guys is divided by n, but then this is I, this is basically, this is 1, when I equals 1, this is when I equals 2, it's 2, when I equals 3, it's 3, 4, it's 4, when it's n, it's n. So it's always I. What is this equal to? Well, we need to pull out the 1 over n, summation I equals 1 to n I. You guys should know what this is in closed form. It's equal to 1 over n plus what? And so then these n's will cancel out, and it's equal to n plus 1 over 2. And so the average case is going to be some n times some constant. And because it's n times some constant, that means it's going to be big O of n. And so that's what you can go ahead and do to show that this doesn't have a very good runtime, even in the average case. And so if we're inserting linked list and we're not doing duplicates, it's actually not going to be 1, it's going to be order n. So linked lists, depending on how you're doing this, can work really well, or it can work really poorly. All right. Now, before we go to amortize, we're going to talk about the delete. And so the ones we're talking about is the unsorted array list, and we're doing duplicates allowed. So with an unsorted array list and we're doing duplicates allowed, what's going to be the runtime to delete on average? Yeah, it's going to be n. What about the worst case? It's going to be n as well. That doesn't seem very good. Hey, what's the best case runtime for this though? All right, I heard someone say n over 3. I also heard someone say 1. Maybe 1. All right, who here thinks it's 1? Who here thinks it's not 1? Few people think it's not 1. All right, so in the best case scenario, so does someone want to argue why it's 1 for those that say it's 1? Yeah. All right, so then if it's the first one, you just remove it and you're done, right? All right, but the thing is, there could be duplicates. And remember, when I remove Joseph, I need to make sure I remove all Josephs. So if there's like 17 Josephs working and I remove 16 of them, I'm not done yet. I need to keep removing. And then even if I remove 17 Josephs, my program doesn't necessarily know how many times Joseph occurs inside this list because there's duplicates allowed. So I need to keep going until I eventually hit the end. What I need to do is I need to be able to go through every element in this list and check to see if it needs to be removed. Which is crazy, right? So the best case scenario is actually still n. And the reason why is because even if it's the first element that I remove, I might need to go to the next guy. And I need to keep going and keep searching until I find it. And this is why duplicates allowed is kind of a really bad idea when you're doing one of these lists. All right, what about an unsorted array list? With no duplicates. What do you guys think the runtimes of this is? Average, worst case, best case? Yeah, it's still going to be n for these two. Yeah, the best is now 1. But the reason why this is better though is because even though it works better in delete, in the insert it actually works poorly. And the reason why doing unsorted array list works poorly with no duplicates and you're doing insert is because your best now needs to be order n. Because what you need to do is you need to check to make sure that that element doesn't exist before inserting. So there is actually a trade-off between this and the insert. That's like really a minor thing, and that's not super important to like have like memorize. Like it's just kind of like something that ends up happening. There's like a lot of these weird things that end up happening when you do computer science, unless you're like working with balance structure, and then basically you're sacrificing code like readability for usage or efficiency. But anyways, so then the next thing that we should talk about is the sorted array list. And we'll assume that this is a no-do, or no, we'll do a duplicate allowed. All right, so if you have a sorted array list, what's going to be the average case runtime for removal? So it's actually going to be really bad. It's going to be order n. And the reason why the average is order n is because once you remove the element from the list, you need to move back every element that has been, after it. Because you need to keep it in serialness of the array list set up. What you could do, I guess, is you could like flag a value that's saying, hey, that element's no longer here, which means that you need an extra overhead of memory. But then that's like kind of problematic because imagine you have a company that's been going on for like years and years and they keep hiring and firing employees because they have a really poor turnover rate. Google. I'm kidding. But the thing is, like, if you have all these employees that are basically dead employees in the system, and you're just saying, hey, these people are not people that you should pay attention to, then you could end up like having issues with memory management, where you're using up too much memory. So the answer is you could do this in log n if you had a secondary array, but then the issue is you're going to have a lot of extra memory being stored around that you're probably not going to be able to clean up unless, like, periodically you perform purges where you just go through the entire system and delete all the employees. But that would be like a really advanced data structure. And it'd be cool if you guys coded that up, but it's not really required in this class. So really, without purge, and no mark for deletions, this would be big O of n. And then the worst case would be big O of n as well. And then the best case would be what? So the best case actually in this is big O of log of n. And the reason why the best case is big O of log of n is because if the guy doesn't exist in your list and you're trying to delete him, then you don't have to do anything. Like, you just search for him and find out he's not there and you're done. And this is assuming that duplicates are allowed. You can do that. But this is like a really weird thing to describe here. I might end up coding this up for you guys because that's a fun thing to do if I have the time, which I do have a little bit of time. But I do need to go over amortized. There's so many things to talk about. All right, so then we'll talk about binary search trees. So binary search trees, what's the average runtime? I can pretty much change that to whatever I need it to be. So who thinks it's n for average case? Good. Who thinks it's only 1? Okay. Who thinks that it's 1? Okay. What is it then? How many of you guys voted? N squared? No. It's N. What about the worst case scenario? So when you're trying to remove something from a binary search tree, this is the non-balanced one. What's the worst possible situation you can have for doing the removal?
This is a balanced.
This is not BBST. This is just BST. Yeah, it's going to be N, because you have to go all the way to the end. And the best case is going to be what? Log of N. Unfortunately, there's not much getting around in that. The BBST is going to be big O log of N for everything. And then the last thing is the linked list. Linked list deletion is really bad. If it's the first element and there's no duplicates allowed, then that means it's going to be big O of 1. But if there are duplicates allowed, it's going to be big O of N. And the average case is going to be big O of N as well. So I'm going to go ahead and end it here for talking about just the runtimes of these different implementations. I think that you guys could probably very easily do some of these on your own. What I really want to talk about right now is the amortized runtime, and why is that useful? So, amortized runtime is a really weird concept, and we can think of it as like, even though you're going to be doing some things multiple times, some of all the things you end up doing is never going to be worse than some given amount. Like there's going to be basically some summation that you're going to get to where all the values are going to be no worse than that large summation. And one example where we have like amortized runtime analysis is we're working with the quick sort. And then that sounds like really weird, but when we're working with a quick sort, at any one level, you could have multiple different number of operations you end up needing to perform at some recursion level. So the idea is that all the operations that are performing at each recursion level is going to be no more than n. And so even though at some particular instance, you might have n, and you're like, oh, but there's going to be like a logarithmic number of these, in which case this is like entire thing, or there's an exponential number of these, and because that's going to be some exponential times n, and it's going to like be really bad performance or something like that. But it ends up not being that bad because the sum of everything ends up being very small in comparison to whatever you're given. So the idea of amortized runtimes. So when you have something that's amortized, that means that you can go ahead and say that the sum of all the runtimes is going to be no more than some smaller amount. So when we were talking about this in class today, we were talking about the array list. And we were talking about allocating memory for the array list. So the idea of the array list allocation of memory is that if we're always increasing memory, we're never decreasing it, we need to think about how much runtime it's going to take for doing this allocation with respect to everything. So when we have an empty array list at first, imagine that we have only like a size of 1 value for this array list. And you can imagine that this is basically a garbage value. It's effectively empty at this one particular spot. What we end up doing is we insert a value into this array list, and we fill in this one spot. You can imagine that the size of the capacity is initially 1, but the capacity is initially 1, but the size is initially 0. So we can add one element, but we won't be able to add a second element without doing something tricky with the memory. So inserting one element, this is size of 0 and capacity of 1. So inserting one element, we're able to go ahead and change this to the array of 1, and now our size is equal to 1, and our capacity is equal to 1 as well. When we insert the second element into this array list, what happens is we need to go ahead and resize this, because unfortunately the size and capacity are equal. So when we insert, this is 1. What we need to do is we need to resize this. So what we do is we go ahead and take all the memory that's in there currently, and we copy it into some new larger array that we end up allocating. And so we increase the capacity, and normally what we do with this capacity increase, like if you pay attention to what I did earlier in the class and one of the very beginning lectures, what we did was we took the capacity and we multiplied it by 2, and we added an additional 1 to it because I was worried about this like special case. You don't really need to do this add 1, it's fairly optional. But it's useful if you're dealing with the things that are potentially 0 capacity. And then what you end up doing is we have to update the size as well. And so the size would end up being 2 at that point. And so imagine we had this thing here that's now 1, 2, and the size of the capacity was 3. This would be an empty spot. And so this first insertion here took only order 1 time, but this insertion here took actually order like n plus 1 time. And so like this was like a really quick one, and this one was a really slow operation. How much execution time are we going to need, or how many operations are we going to need for inserting the next element, for inserting 3? Yeah, we're only going to need 1 operation. So for inserting 3, it's really easy. This is like big O of 1, not bad. This is unfortunately like 3 operations that we potentially need to do, maybe 4 if you want to think about like you have to actually insert the value. This could be really, really tricky. But then inserting 3 is pretty easy. And then when we insert the next value, like what do we end up having to do? Like how many operations? Well, we're going to have to resize the array, which means we're going to need to find a new spot for allocating the memory, and then we're going to need to copy the values in there, and then we're going to need to insert this new value. And so this is going to be a lot, like you can imagine like it's big O of 6 or something like that, or not big O of 6, but like 3 operations, which is like big O of n. This is going to be about like 7 operations maybe. And this is like big O of n as well. And so like you see like these big O of n operations occurring, and you're like, oh man, the worst case is going to be really bad. The worst case is going to be big O of n. And you can say, yeah, the worst case does appear to be big O of n, but the thing is, it's these operations that we end up doing end up being few and far between. And the reasoning why is because after we resize this element by inserting the 4th value, so we have all these empty spots, and all these empty spots are going to make it really easy for doing these insertions. The next 3 insertions are going to be really, really quick, and they're going to be very painless. So if we think about it, the total amount of runtime that we're going to end up taking is going to be like 1 plus 3 plus 7 plus, and the next one's going to be about 15 number of operations. And these are going to be up until you get to around n. So ... n. And this is going to be how much to do all the resizes. And so I'm just looking at the total number of operations it's going to take. And this is always going to happen no matter what you have. This is best, worst, average case, what have you. So the resizing operations, it's going to be looking like this. The total number of operations you do every other time, which there's going to be about n of those. And the reason why I say about n other operations is because there's like really n minus log of n. But n minus log of n, this is like a really small term, so we don't really care about it. It like goes to 0. And each one of these other operations take big O of 1, or about 1 operation to do. So it's not very expensive. And so if you actually do the summation out, you'll actually end up finding that this is something that is, as I mentioned before, a geometric series or geometric sum. and it's going to end up turning into something that's no more than 2 times n, which is really convenient. And because we know that this is no more than 2 times n, and we know that really you could actually say that this could potentially go out to 2n, so if you wanted to be even more correct or a little bit more pedantic, you could say that's less than or equal to 4n. And all the other operations is going to take no more than like c times some n for the total number of operations. So the total number of operations, or for the total number of other operations, the total number of operations should end up being the sum of these two. And so all the operations should take about 4 plus c times n. And this is like just a constant. And because this is a constant, we can say that this just is in big O of n over all the different operations. And because all the operations are going to be n times 4 plus c, then that means we can say the average number of operations we're taking is about 4 plus c operations for any one in particular operation. Amortized. And the reason why is because if you go ahead and just equate this for every operation, we consider that over the course of the entire program, this is going to be effectively what we're having in the worst case scenario. So this is like it doesn't occur very often when we're using this amortized. Another situation that happens, which you're not going to see until much later, is in disjoint sets that's used if you're using what's known as the path compression. But this is really a CS2 topic, so many of you guys won't be exposed to that. I might end up talking about some amortized thing on an exam though, so you guys need to be prepared for that. But really what you can think about is you try to find out what the total number of operations are for the entire execution of a program, and then after you find out what the total number of operations are for the entire execution, you can go ahead and use that to figure out what the average is, or what the worst case average is. Let's see. All right, so the last thing I want to go over before leaving, there's like one other thing with sets that I actually haven't gone over yet until, well, now, which is sets need to be able to be iterable, which is something that people really like to have the ability to do. So does anyone want to take a guess as to what iterable means? Yeah, you can iterate through each element. I mean, again, iterate is like a word. I feel like I just recursively defined this in like the worst case scenario. There's no base case. What I mean to say to iterate is I want to go through each element. I want to be able to output it. I want to be able to output it exactly once. All right, so let's go ahead and think to a really horrible example, which is why we're never going to probably use this in practice. We're going to go ahead and think of the array that I'm allowing the duplicates to be in. And it was unsorted. So how would I go about going through this array and iterating through it? You can imagine that maybe I want to just create a roster of employees, so that way I can go ahead and have that printed out for my maybe tax purposes or something. Maybe claim them as dependents because they're currently my children. Yeah, what's up?
Can't we do it the slowest way possible by outputting it, or taking the entire array, bubble sorting it, and then
Okay, so you're joking, but actually that's better than the other way that I was going to express. So the way we could do it that would be really horrible is we go to the first element in the list, and then we check to see if we've output this before. And how do we check to see if we've output this before? We go through the whole list up until this point, and then if we see it ever again, like inside that list of first couple elements, then I won't output it. Otherwise, if I get all the way to my elements, it'll output it, and I'll move to the next one. And so, what's the runtime of this method? So I'm going to go ahead and check the first element, or I should say check the ith element. If it has been seen before, don't output. So what's going to be the runtime of this in the worst case scenario? No, it's not that bad. It's actually pretty close to what you said in terms of bubble sort. So you can think about it, that the first element, I have to look at 0 elements, right? The second element, I'll have to look at 1 element. The next element, I'll have to look at 2 elements, right? Because I have the first and the second element, and maybe that this is a different element, so I go ahead and output this one. In the fourth spot, I have to look at 1, 2, and then 3 elements. So in the next element, how many am I going to look at? So first, I have to do 0 comparisons. In the second element, I have to do 1 comparison because I have to compare the first element and the second element. The third element, I have to do 2 comparisons. I have to compare the third to the first and the second. What about the fourth element? And the fifth? Yeah, and I think we see the pattern here, right? 0, 1, 2, 3, 4. Up to the end, what's the nth one going to be? All right, and so this summation, what is this equal to? And so if you actually sorted it, in my opinion, you have done something better, because now you have a sorted array and it's easier to find elements inside of it. But we didn't do that in this situation. We just checked to see if it was there. If it was, we didn't print it out. If it wasn't, we did print it out. So this is honestly a really bad way to do it. And this is why doing arrays just in general for sets are a bad idea. But this is how you could go about doing so if you had something that was unsorted. I recommend putting like one of these things up on your own, like implementing an array to do a set. You'll see it's absolutely awful, and then go ahead and do it with the binary search tree, and you'll see it's much, much better to do. And I also would recommend as practice to do an iteration of a binary search tree. It's much easier to do it than with any sort of linked list, in my opinion, or array list. If you have any questions, you can talk to me.